Hello, I am the Mighty Pez. In this video I will discuss noise, an issue common to physical switches, how it affects a circuit, as well as demonstrating an integrated circuit solution for the problem. So please join me. These devices are examples of switches with mechanical contacts used to connect or break circuits, and all share the same issue: noise. To demonstrate the issue that this causes, I have assembled a simple circuit that consists of a momentary switch connected to a 74393 series binary counter, which will trigger on the falling edge and will display the result on connected LEDs. For our test, we will reset the counter and begin by pushing the button 15 times. Our expectation was that 15 key presses would advance the counter 15 times, and we would see 4 bits enabled on our counter. However, as you can see, the counter has rolled over and produced 5 undesired triggers. We will now look at an oscilloscope trace so that we can visualize what is happening to the signal that is causing our issue. To facilitate this, I have attached probe leads to the output of the switch and output of bit 1 of our counter. We will trigger on the falling edge of our button. This shot shows a brief spike 80 microseconds before the expected trigger, producing an erroneous double trigger. The next shot shows ringing, which caused 2 state transitions erroneously on the rising edge. The third shot is a particularly ugly example of an unexpected spike and ringing, leading to 2 unwanted state transitions in addition to the expected edge trigger, all occurring within about 200 microseconds. Mitigating the issue is referred to as debouncing. There are a couple of ways that we can look at mitigating. If your circuit is microcontroller or microprocessor based, you can solve the problem through code logic. If your circuit does not contain a processor and does not require complete mitigation, a simple solution such as running the signal through a Schmitt trigger may be enough to reduce the side effect of ringing. Although this may not remove all bouncing, this may satisfy a use case such as an on-off toggle button, where occasionally pushing the button multiple times to put the circuit in the correct state is acceptable. I have a video where I describe the Schmitt trigger, the property of hysteresis, and how it can reduce circuit flapping. For a counter circuit, where we do not want to overcount state transitions, a more robust circuit solution such as a resistor capacitor or RC circuit may be needed. RC circuits have the benefit of being widely implemented using simple and readily available components, and many examples on the web using RC circuits for debouncing can be found. However, for this video, I will be focused on discussing a general purpose built IC that I came across and have used in several of my projects: the LS10 series debounce IC from LogiSwitch. The LogiSwitch LS10 series consists of 3 options: a 3, 6, and 9 element IC. The LogiSwitch LS10 series as a solution has the twin benefits of simplicity and reduced pin count as compared to an RC circuit. The trade-off is simplicity over cost, as an RC circuit can be built for pennies in bulk. However, for the hobbyist who is working in low volume and needs a reasonable number of debounced inputs, the cost per debounce element is reasonable, approaching 50 cents with the higher pin count devices. With my projects to date, pin count is my primary budget requirement. The LS10 series IC has a simple wiring diagram. The input pins are directly offset from the outputs. Please note, however, that the power and ground pins do not follow the same convention as one comes to expect with most 74 series ICs. Power comes in on pin 1, and the highest pin number, the pin directly opposite pin 1, is ground. Missing this detail will cause operational issues. The LS10 series IC achieves switch debouncing by delaying both rising and falling state transitions for 20 milliseconds. This allows time for any ringing to settle and will prevent a spike of anything less than 20 milliseconds from causing the output to change state. Here I have modified the test circuit to include the debounce integrated circuit. As you can see, I've added the LS18 3-element variant to the circuit. I then took the same noisy switch output and ran it through the debounce IC prior to feeding the second 4-bit counter element on the 74393. This output is fed into the rightmost 4 bits of the LED. To demonstrate the functionality of the debounce IC, I hooked the oscilloscope to the circuit, placing the red probe directly on the output of the switch and the yellow probe on the post-debounce output of the 74383 counter. The oscilloscope is initially set at 20 millisecond per division, and you can see that the counter is triggered 20 milliseconds after the signal goes low. To make the noise more evident, I have decreased the time per division, thus zooming in. You can plainly see that this single button push resulted in multiple spikes in the first 2 milliseconds after trigger. If the physical contact noise of the button press had not been ignored, this would have resulted in multiple triggering of the counter. To test the LogiSwitch IC and demonstrate the results of debouncing, we will push the button 15 times. As before, the goal is to trigger the counter 15 times and set all 4 counter bits high. After the test, we can see that the right 4 bits of the LED are set high, meaning that the counter did increment exactly 15 times as desired. The left side of the LED shows the results of the original circuit, which triggered the counter directly from the noisy switch. This counter shows that it was incremented an undesired 3 additional times. I have also used this switch in projects where I may not need debouncing, but rather want to add a fixed and non-inverted signal delay without adding the timing variability or increased pin count of a chained inverter, such as a 7414 Schmidt inverter. As mentioned in the video, for my current projects, my overriding budget concern is reduced pin count and simplicity, not component cost. Thank you for watching this video. I hope it has been informative and provided another option for debouncing circuits.